All right, it's 12:02. Let's get started. I'd like to thank everybody for joining us today for our battery fundamentals and troubleshooting webinar. This is a first webinar in a series that we hope to present over the next few months. And this one's really designed to give you the basics to get you excited and involved in some of the battery technology and a little bit of primer as to what you're going to see next. I'd like to introduce our speakers today. Augustin Brochot. Thank you, Augustin. Is the Vice President of Innovation and Strategic Ventures for Trigo. He's responsible for leading Trigo's innovation strategy. Prior to Trigo, Augustin spent over 15 years in R&D manufacturing, purchasing, and supply chain with Stellantis, formerly PSA, and 5 years with Boston Consulting Group in the industrial goods sector. Our subject matter expert today is Attila Vitosh. Attila is our global battery and new energy vehicle expert, specializing in operational management, quality management, and engineering services. He has over 25 years in the automotive industry in the areas of quality and project management at several tier 1 suppliers. And as your moderator today, I'm Lori Powell, responsible for Trigo's consulting and engineering services portfolio in the Americas. Before we begin, I'd like to spend just a moment introducing you to Trigo. We're a global provider of operational quality management and supply chain solutions. With over 35 years experience, our 10,000 employees in 29 countries offer a complete portfolio of services throughout the supply chain. We understand that managing a global supply base requires support in meeting quality expectations. Trigo's focus is ensuring quality throughout the supply chain by carefully selecting and training our teams around the world to provide practical approaches and customizable solutions. We support our clients globally by providing quality professionals with a skill set and personality to match their culture in some of the most demanding environments. Our teams around the world work on short and long-term projects. They could be brought in to supplement or augment your staff to ensure processes, materials, assemblies, and components meet the quality design requirements needed. Through our on-site inspection teams, resident engineers, technical resources, performance improvement consultants, auditors, and training programs. Now let's get into the agenda for today. So today, the contents of this webinar, we're going to go over some industry trends, BEV, PHEV, HEV, different types of battery technologies, key components, manufacturing and quality, life cycle and safety, opportunities, and then a question and answer session. So if you have questions, please feel free to put them in the chat. I will be seeing those and we'll be able to address those at the end of the webinar. If we have too many questions, believe me, we'll make sure that we get answers back to you. So we're going to try to capture as many of those as we can. With that, I'll say thank you very much for attending and take it away.
Yes, thanks a lot, Laurie, for this introduction. Let's get into the first chapter of this webinar, the EV industry trends. Yeah, so globally, what we see in terms of EV trends, so it's a global growth of 27%, which is expected in 2024. The 3 largest markets are China, with more than 50% of the global market, then followed by Europe, with more than 20%, and then North America, with a bit more than 10%, close to 13%. Those are the 3 key largest markets globally. EV sales in North America are expected to grow by more than 30% in 2024. And if we look at EV sales in the US, we had an increase of around 60% in 2023 versus 2022. All this growth of EV global sales has also an impact, and we see some improvement in terms of technology, in terms of product, as well as manufacturing process. And this volume increase, we see globally a drop in EV battery prices between 2023 and what we do forecast as 2025 by 40%, which is a key element to get much more affordable EV car. Moving to the main type of electric vehicle. So basically, there are three main electric vehicle system architecture today in automotive. So we have the battery electric vehicle, the plug-in hybrid electric vehicle, and the hybrid electric vehicle, which I will briefly introduce right now. So basically, a battery electric vehicle relies only on a battery and electric drivetrain. There is no internal combustion engine, and the key energy storage is the electricity, which is stored into a large battery pack. This battery we can charge by plugging into the electricity grid, and that's the way we get power into the car. Moving to the next one, the plug-in hybrid electric vehicle. This one has both internal combustion engine and electric drivetrain. It can be powered by fuel, as well as it requires also a rechargeable battery pack. This battery can be charged with electricity by plugging into an electrical outlet or a charging station. So this is key. Roughly, what we can say is that the driving range for such vehicle, the driving electrical range, is quite limited. For the plug-in hybrid electric vehicle, it's between 40 and 60 in electrical mode. Then the last one is the hybrid electric vehicle, which is also called standard hybrid or parallel hybrid. This one is quite similar to the previous one, except that there is no opportunity to plug in to charge the battery. The key element here, the battery gets charged only with the motion of the wheels, and that's the key to charge. When we decelerate, there is opportunity to charge, and this one has no charging port. So those are the three types of main electric vehicle. If we look now, if we deep dive into the primary source of energy that is required for each of those powertrain system, the first one for the battery electric vehicle basically does require high energy density. That is required for the battery of this electric vehicle. This energy density is key for different purposes. One being the drive range, the autonomy of the vehicle, or to reduce volume of the battery or the weight of the battery pack. We see strong innovation in terms of product technology as well as manufacturing process in those battery packs. On the next vehicle, on the PHEV type. So here, what is key in terms of source of energy is the high power performance energy. Basically, to be able to combine optimized energy density at running at a consistent level over quite a long lifetime. And the last one, the hybrid electric vehicle, basically on this one, what is required in terms of typical batteries, the power performance and durability. And that's the type of battery system that are required to get the highest power density in order to absorb and release energy in a high dynamic mode during both the drive mode and recuperation mode. That is to say, when we do brake in order to get this energy to recharge the battery. Now, deep diving into the key elements of an electric vehicle. So starting with the OBC, so the onboard charger on the bottom left of this chart. So that's basically where we do plug in to charge the battery, the electric battery. Then above on the top left, the power electronics. So here are some key elements that are required basically to manage the energy that is provided, that is needed between the battery provided to the electric engine. So some example of components, key components are the inverter and converter. Then the electric engine, which converts the electrical energy into mechanical energy. So there are several types of electric engines. So there are some permanent magnet, there are some switched reluctance or AC induction. And then the e-transmission, which is much more simple with electric engine than with ICE, internal combustion engine. And finally, the key component, what basically drive the cost, what is a key driver of the cost of an electric vehicle, that's the battery pack. And that will be the focus of the next slides. So a battery pack, basically, so you can see on the right of the slide. So this is basically a compilation of battery cells, which is the smallest units that store the electric energy. And those cells are arranged into modules that are assembled into battery packs. These battery packs has some specificity. Basically, the shape of the battery packs is key and has to be customized to the vehicle so that it can be assembled to the chassis of the vehicle. And we'll get now into the next chapter, the battery product and the key component of the battery packs. So we have three levels of the battery key components of the battery packs. So we can see there are three levels of batteries. So the smallest unit being the cell level. Second, which we have in the middle, is the module level. And then the battery pack itself, which is assembled to the electric vehicle. Starting with the battery cell, so that's the smallest unit. So the key components of the battery cells are the cathode and the anode, then the separator and the electrolyte. So that's where we do have this chemistry to charge and discharge. And that's multiple cathodes and anodes, so that are stacked together. There are three types of forms, physical forms of cells that are commonly used in automotive. So it's prismatic, cylindrical, pouch, and we'll get back to this right after we'll deep dive into this different type of cells. Those cells, what is key is that they are what we call secondary cells, and we can recharge multiple times. So that's what makes the life cycle of a battery. Then we have the module. So the module basically is multiple cells which are connected together, either in series or in parallel. They are connected with what we call a bus bar, a metallic frame, in order to make a connection between the different cells. These modules are compact, rather stackable design. It's robust, and and that's, I would say, some of the key points. The laser welding is key to make the connection between the different cells. And then inside these modules, there is a PCB, small printed circuit board, some electronic, in order to be able to manage both the temperature of each of the cells as well as the voltage of the different cells. Then finally, the last level, the biggest level, the battery pack, which is used either for different type of vehicle, could be for hybrid or battery electric vehicle. So that's the one that supply the energy to the electric engine. The architecture of this pack, it's connecting similarly to the modules that connect the different cells. The battery pack connects different modules, and then it includes, I would say, the computer as well. that manage that monitor the energy, and the different cells and the different modules. It does include thermal management system in order to cool the battery, as well as a strong housing structure in order to protect from vibration, shock, the different cells. This battery pack has to be designed and tailored for for the chassis of the vehicle, so for each vehicle platform. So that's key. And some key parameters are performance of the batteries, the safety, and the life cycle, which is critical for this overall performance. Deep diving now into the different type of cells formats. So as mentioned, there are three. First one being the cylindrical cell. So those one are the historical. Those one are also the one that we are used to for I would say other markets than automotive. The shape. So basically, we have the bottom part is often the negative terminal, and the top center the positive terminal. This is also what Tesla used at the very beginning. And so it's inside, it's alternating rows, round body elements, anodes, cathodes, and separator are encased tightly. The second one being the most popular one today, and also as forecast according to the forecast for the upcoming years. So these one are the prismatic cell. So it's a rectangular box that you can see on the screen. Electrodes are mounted in a rigid aluminum casing, and there are basically two types of inner packing. Either a flat one type where the battery is rolled flat, that's also called the jelly roll. And there is also the stacked laminated type where the electrode and separator are stacked one on top of each other. And then the last one, it's what we call the pouch cell. It's rather a flexible, soft construction, and it's adaptable size, mostly flat, rectangular, rather simple, lightweight solution for battery design. Deep diving now, once just introduced those three types of cells. Now let's get into what are the pros and cons for each of those. So cylindrical one, as mentioned, is rather the historical one, and is quite used also by several OEMs. They would use different cells formats depending on the key requirement and the use cases they are targeting in terms of safety and performance. So starting with cylindrical one, basically what is key here is availability on the market that's historical, and the cost effective to manufacture. So this is one key element. Second one is this shape is allowing also this shape some cooling pathway between the cells when we do assemble the cells into modules and packs, which enable good thermal management and performance. And finally, the last one is the mechanical stability thanks to its circular design. Cons related to these cylindrical cells. So due to this shape, it's difficult to optimize the volumetric efficiency into a pack when we stack them next to each other. So that's one key element. And the second is the energy density, which is rather lower than other cell formats. Moving to the prismatic cell, so the most popular one. So format is rather can be larger and with a higher capacity, which enable to have less cells into an entire battery packs. So maybe a better efficiency when we do assemble those cells into battery packs. Then the stacked configuration can facilitate the heat dissipation and temperature regulation. And then the volumes can be easily optimized because we can stack those cells, those rectangular cells next to each other in order to optimize the space. So that's really some key element. And last but not least, the enhanced safety features with that can offer those prismatic cell. So two cons. So there is more potential stress for parts of the electrode and separator sheets that are close to the case corner. So that's one cons. And the second one, the cells can be more expensive to manufacture. Finally, the last cell format, the pouch one. So two key pros. One, which is they are flexible. So we can basically easily custom or much more easily custom the shapes of such a cell to fit to specific application. And the second key pros is the lightweight of such a cell that makes them efficient. On the cons, so the poor thermal conductivity of such cell is clearly a disadvantage, and the lower mechanical resistance. So that needs some strong protection against external impacts or punctures. Moving on to the next slide on the battery pack parameters. So basically we have some functional parameters such as cell, if we look at the main one, so cell voltage, then some performance related to capacity and energy. So those are some key performance parameter for the cell. And then some related to the status of charging, related to the loading of the battery, the charging of the battery. So that's the state of charge, and then the opposite measure, opposite parameter, which is the depth of discharge. And then we have some charging profile key parameters. So the voltage limitation, that will be key, the key element to enable either a fast charging or the speed of charging. And then the last one, the state of health, which is key related, a key parameter that gives you where it stands, where the battery stands in terms of life cycle. So this is a key parameter. The state of health typically for automotive will have some good performance between 80 and 100% of state of health. So that will be the first life of the battery. And then it can have another life, a second life, lowering this state of health from till 50%. And then it will be okay for recycle below 50%. If we look at the key performance elements that are detailed on the bottom of the slide. So one being the energy density, the gravimetric energy density. So that's basically the power per kilograms. This is driven by high nominal voltage, high ampere hour capacity, and low mass. And the second key parameter is the volumetric energy density, which we do measure watt hour per liter. Now, I do suggest we move on to the manufacturing processes and quality. So to give you an overview about manufacturing process. So starting with battery cell, so the smallest unit of a battery. So here we simplified the manufacturing process into 3 steps. So electrode manufacturing, cell assembly, then formation and cell finishing. So electrode manufacturing, basically it aims at manufacturing both anode and cathode in parallel. And what is key here is the environment in which we do manufacture those electrodes. We really need to avoid any foreign particles in this process, because that could be causing some failure, some issues moving forward, even some safety issues. So that's really key to work in a very clean environment, in a clean room condition. Then the cell assembly here, basically aiming at stacking the different anodes, cathode, separator together, and then filling in with the electrolyte plus some components. And we need to seal to do also the sealing of this cell. And here, what is key is to avoid any humidity inside the cell leads in order to avoid any severe quality issues. Finally, we have the formation and cell finishing. And here there are I would say, lower specific requirement in terms of cleanness or humidity. But that's, yeah, and that's about it for the cell. Once we have a cell, basically we can move to the next level, to the battery module. Here we listed a few key steps. So the cell stacking, the cell stacking into the module, the assembly and welding of those assembly of the cells, and welding of the metallic frame in order to make the connection of those cells. Then the end of line testing, so different components, of course, mechanical components, then the end of line testing, then some key elements related to labeling in order to ensure the traceability, quality inspection, and then the packaging of the modules. So those are some key steps related to battery module manufacturing. Then once we have now that we have the module, we can move to the last level, so the battery pack, which we detailed a bit more. So here we start with basically the pack housing and the cooling system, placing also the electrical insulation with some thermal interface material. So it's key to be able to cool those batteries. Then we'll insert the different battery modules into this battery pack housing, and then we'll move to several mechanical components, so the thermal management unit, the battery management system, and the high voltage distribution unit. So this will be some key element to place that will make basically the connection between the different modules in order to connect the battery packs. Then we'll move to basically the lead assembly to the base, the sealing of this battery of the battery pack. And then a key element is also the leak test. The leak test in order to avoid any issue in the cooling circuit. After that, we can charge and discharge the battery according to different performance profile. And finally, we'll get to the state of charge, the desired state of charge, before having the software update into the battery management system, then the end of life test to confirm that everything works properly in terms of electrical performance. And finally, we'll get to the outgoing inspection, so including labeling and then packaging. Of course, here we did not outline, but there could be some pre-work activity if one of the check at the different step is not okay. So those are the key steps related to manufacturing process for cell, then modules, and now pack. If we have now an overview on the quality parameter, some key elements related to inspection, whether it's related to manufacturing of the battery, or whether it's related to the life cycle of a battery and inspection during the life of the battery. So basically, we have some inspection at different level of the battery, at cell level, at module level, and at pack level. Here, the quality control plan include different type of inspection. So dimensional one, some mechanical one, some functional one. Of course, the identification is key of the battery. Appearance is key. We'll get into this. Electrical performance. And there are some safety check, leakage check, also some communication analysis in order to check that we have the relevant software and to analyze the different potential DTCs with that coming from the BMS, the battery management system. DTCs being the diagnosis trouble codes, defect trouble codes. So then the cell quality parameters inspection. So if we deep dive into the first level, basically there are 4 types of checks. So the dimensional one, the functional one, the cell appearance, and the identification. So here, if we look at the functional cell check, so we'll measure the open circuit voltage of the cell, confirming that it's consistent with the nominal expected, the DC internal resistance, the temperature, which is key related to a cell. Then we look at the cell appearance also, making sure there is no scratch or dent on the cell, which could be a mechanical issue. Basically, if we see a dent, there could be a short circuit inside because it's a stack of anode and cathode. It could be, for example, 80 anodes and cathodes inside one cell, just to illustrate. So any dents basically could be an indication of a short circuit inside or a risk of short circuit. Moving to the module quality parameter inspection. So here we find similarly some dimensional check. So weight, dimension, checking as well the bushing dimension. Then electrical performance check. So including the voltage, internal resistance, open circuit voltage, which also gives you an indication related to the state of charge. Then the temperature. In addition to the module appearance here, also we'll have another one, which are the safety tests. So here there are two key tests, one being the dielectric strength test, and the second being the insulation resistance test. So those ones are done operating a high voltage peak and looking at the behavior of the battery. So both the insulation resistance and the dielectric strength. Then at pack level, the key parameters inspection are the following. So performance and safety check. So that's of course the end of line and electrical performance check, including voltage, leakage check. Of course, we want to avoid any leakage issue of this battery for the cooling system and avoiding any impurity inside, and the isolation test. Then related to the battery management system, so communication analysis, basically being able to read different fault code, and that gives you how the battery is performing and the battery state. And finally, appearance check. I do propose now to go to the next chapter. So life cycle and safety, which are two key elements when we are looking at EV battery. So starting with the battery circular economy. So here we simplified, but gives you a quite indication for 4 key steps for a battery life cycle. So the first one being the design and manufacturing of the battery, so battery cell, module, and pack. Then we go to the first life, which I mentioned, which can be automotive. So where we have typically state of health between 100%, and we can go up. We can go to down to 80%, 75 or 80%. Then we do have the second life for a battery. So typically could be a battery energy storage system. So for stationary equipment, for example, for a solar panel, for solar panel storage. So the second life, we would go from 75, 80% down to 50%. And then the next key steps is the recycling, so that we have here an opportunity to recover some scarce material, such as lithium, cobalt, nickel. So that's typically what we call the black mass, in order to reuse those key scarce material for the manufacturing of new ones. So the key benefits of such battery circular economy is, for sure, one is improved carbon footprint. Second is to be able to maximize the life cycle of the battery, focusing on first life, then second life, and then the recycling, enable to access some scarce material. So these are some key points. To be noted, there are some requirements depending on the region for regulatory and depending also on the client, the final customer. So there could be some specific requirements as well. Moving on to safety. So basically, batteries, I mean, it's not a standard mechanical component, as you have understood. So they can be dangerous in only in specific cases. And these are listed under the hazard. So those cases are overcharging of a battery, short circuit inside a battery, as mentioned, then exposure to extreme temperatures. So this is also a key element, or thermal runaway, some physical damage, or manufacturing defects, aging, degradation, or improper storage. So those are some key hazards that could lead to basically the main risk, on which we have seen few occurrences. Hopefully, it's very few, but few occurrences which could be a fire. And when such battery goes fire, basically it's quite complex to stop the fire. So it's just taking a long time to consume all the chemistry inside, and till the end of the fire. So salty water is the key, but that's basically taking some time. Let me now hand over to Attila Vitosh to deep dive into potential hazards.
Thank you, Augustin. I would like to share an example of the importance of lithium-ion battery safety and the potential hazards surrounding them. At the manufacturing facility, battery cells that were being manufactured and charged to 30% SOC, this is the delivery SOC level of the lithium-ion batteries in automotive applications, had to be checked and to meet the final quality specifications prior to delivery. Due to a lack of storage and control space, the reevaluation took place in an empty area where the assembly work also occurred. Out of the curiosity, the workers were looking at the prepared battery cells. One of the workers mistakenly dropped a hand tool on the top of the cells, and it caused a short circuit. The short circuit triggered a thermal reaction, which caused at the end a fire. The workers were not trained in the potential dangers of handling lithium-ion batteries. They panicked and ran out of the facility. Fortunately, the facility had fire and smoke detectors, which were immediately set off. Firefighters get there in time before the fire spread to other parts of the hall. The lesson learned of this story is that all personnel, no matter what their role is, should be fully trained upfront and aware of the safety regulation and potential risk associated with lithium-ion batteries. Not only they be trained in potential lithium-ion battery dangers such as electrical, thermal, mechanical, and chemical hazards, but also personal protection equipment. And of course, take the governmental regulations required in working with them. This also includes training how to recognize signs of battery damage or malfunction and what actions to take in such situations. Implementing lithium-ion battery safety measures and knowing the risk associated with them can help ensure a safe environment for everyone. So on the screen, you can also see some really potential hazards, safety measures. But yeah, this storytelling or this explanation, I would like to keep in mind that lithium-ion batteries have to handle in a safety manner. Thank you very much, Augustin, and I will give you back.
Yeah. Thanks, Attila. I think that's really important point. So, basically, we cannot manage batteries as we do manage mechanical components. Those are very. This can be quite a risky component if we don't handle properly these components, especially during manufacturing of the batteries or during inspection or repairing such components. So moving now to the next chapter, opportunities. So just briefly, what we can get here, what we see in terms of opportunities. So as mentioned on the battery circular economy slide, so here what we see as opportunities first, refurbishing or repairing the batteries. So that's a way, basically, there are some damages which you can repair. So we've seen that basically a battery packs is based on several battery modules. So if one module is damaged, basically we can replace the module. Of course, this depends on the conception of the battery packs, but that's typically the type of repair that we may conduct. Or reflashing the battery management system with the relevant software, or some mechanical component exchange. So that's the first opportunity, and that's what we will look for at first, is to repair the battery when there is a battery damage. So diagnose and then repair if it's worth it. Second key element is to repurpose the battery, and basically if the battery has no more, not anymore the required performance for automotive, then would be to confirm its eligibility for a second life for a stationary energy storage system, which can be easily combined with renewable energy. So this is key because this enables to basically maximize the value of the battery itself. Instead of, even though it's not anymore eligible for a first life, we can still extend its life cycle with a second life and then maximize the value of the battery itself. And finally, when it's not eligible for a second life, then we'll go to the recycling of the batteries in order to basically access the scarce materials and reduce also the dependency on new materials for the gigafactory which manufacture those cells. If we look at the benefits of second life EV batteries, so basically it does enable to reduce the number of EV batteries that needs to be recycled, and we have a better value from the second life ones than from the recycling. Typically, some OEM would be paying for recycling battery module still as of today, whereas from second life they can get some income from selling those defective batteries as second life. So that's a key value opportunity depending on the market of the second life battery. Then it does lower the total carbon footprint of batteries in the supply chain. It does provide some solution for the grid infrastructure, and then it's lower energy storage system cost for consumer as well. So such battery energy storage system would be the key driver of the cost of such system is the battery. So accessing a second life battery gives a lower cost, a cost advantage. And finally, it's a way to increase the used car values. So that's why, this is really a key opportunity, this second life EV batteries, and the battery energy storage system market and development is key to get access to such value. Laurie?
Thank you very much. So I appreciate the information that you shared, Augustin and Attila. So what's next? Although there is an industry cooling that we've seen recently, it does allow for an opportunity for companies to take a step back and look ahead, try to stay ahead of the marketplace, take time for a broader look, and engage with the right partners. So we've got a couple little points here that we thought were very relevant to take action, collect lessons learned, refine your strategies, look for those smart investments, improvements, partnerships, and develop some of the right programs. We heard quite a bit about safety, about quality, and one of the the key pieces here is that knowledge transfer, training your employees on those elements of quality and safety, implementing quality gates for the manufacturing processes, and considering afterlife applications. So in this webinar, what's next for us? You can go to the next slide, Augustine. Perfect. Questions and answers. So from the audience, we have a few questions here that we'd like to, I'd like to see, Attila, if we can answer a few of these that came in. Okay, here we go. How long do EV batteries typically last in automotive?
Thank you very much for the question. To give an answer to this one, basically the lifespan of the EV batteries can vary depending on the number of factors, such as battery type, the usage, and the environmental conditions. So the life cycle of a lithium-ion battery in EV application refers to the number of charge-discharge cycles, which and it can undergo before its capacity significantly degrades. Over the time, with repeated cycles, the battery's capacity degrades. This means it holds less charge and provides less energy on time being. So the more you charge and discharge, the quicker it degrades your battery. There are other things that contribute, such as temperature, the charging rate, the design, using patterns, and different chemistries of the battery. So to answer your questions, manufacturers usually talk about the number of years, such as 10 years. They get this number by using a typical number of the cycles. For example, typically might be from 3,000 to, let's say, 4,000 cycles before reaching the end of line in EV application. But I would like to highlight that those batteries still could be eligible for second life application. Obviously, some more durable than others. So basically, many EV manufacturers offer the warranties on their batteries and often guaranteeing a certain level of capacity retention over a specified time and or distance. On SOH level, the state of health level above 80% may be necessary to remain within the warranty terms. As battery technology continues to improve on the market, we can expect even better longevity in the future. Thank you very much. And Lori?
Oh, thank you. Well, we have a couple other ones here. I'm going to flip through, and I think this is one that that we've not only seen here, but that we've been asked quite a few times when we're talking to people about the battery technology. What are the limitations of batteries / lithium ion? So.
Well, yes, they have several limitations. We already touched on safety and cost, but there are several more. I like to focus on two key limitations. One is capacity degradation. The second one is temperature sensitivity, which are more connected to the life of the batteries, particularly in the northern climate regions. So if you are looking on capacity degradations over time and with repeated charging cycles, lithium-ion batteries can experience capacity loss and performance degradation. So basically, this is due to chemical reactions that occur within the battery during charging and discharging cycles. And there are some factors such as temperature, depth of discharge, and charging rate, which can accelerate this degradation. And the last one I mentioned is the temperature sensitivity. So lithium-ion batteries are sensitive to temperature extremes. Basically, high temperatures can accelerate degradation and increase the risk of thermal runaway. And while low temperatures can reduce battery performance and capacity. I hope that I can provide an answer to this limitation on lithium-ion batteries. So Lori, I give you back.
Yes. Thank you. We have one more that that we'll address for those of you that entered your questions into the box. We have those, and we will respond back on those within the next 24 hours. So the last one, Attila, is what causes contamination in battery cells?
Thank you very much for this question. Yeah, this is really a challenging question for the manufacturers. So basically several things can cause contamination, but the more common is metallic impurities. So basically metallic impurities can cause in one way that we call chemical short, where the voltage reduction by self-discharge, and as well as a physical short when overheat and ignition by thermal runaway. However, the manufacturers implement quality control measures which can be put in place during the manufacturing processes to minimize these issues, like in one way the incoming quality control of the raw materials. So basically to inspect the chemical, anode, cathode, conductive materials, binders, additives, other chemicals which is necessary to build up the electrodes, and then the separator, because also it's part of the inner component of the battery cell. Then there are the process quality controls which need to implement it and continuously monitor the contaminants which could come from the manufacturing process. Here, just for an example, impurity in the slurry and the coating. And then, of course, if you have some issues, functional, let's say chemical issues or physical issues, at the end, when the battery cells are fully manufactured, then, of course, with different defects identification, you can build up or you can focus on the failure analysis and to find out from where those metallic impurities comes from the process. Thank you very much.
Thank you. Well, everyone, that concludes our webinar for today. Please feel free to reach out to us if you have any questions. We appreciate your time. And Attila, Augustin, thank you so much for the work that you put into this. We really appreciate your support. Have a great day, everyone.